Now I want to go through a presentation to give you some idea of what we're going to be doing in this class in EECS 622 and perhaps more importantly, why we are trying to learn these things. What's the significance of what we're trying to accomplish? One of the things you might be asking is how is this different than other courses that you have taken or might have taken in our department? Certainly, all of you have had circuits courses of one type or the other. You've gone through in your early circuits classes and you learned about circuits with linear devices like resistors and inductors, capacitors, and so forth. And then in courses like 312 and 412, you added nonlinear devices in transistors and diodes. So if we look at the palette of all of those electrical or electronic elements, we can design some very useful systems. For example, we could put together bipolar junction transistors along with resistors, or at least resistor-like elements, and design a circuit that looks like this. And this is a very famous circuit in electrical engineering. It is of the 741 operational amplifier. It was designed in the 70s and really was the first commercially viable and popular integrated circuit. It really led to the influx of integrated circuits. And so every electrical engineer should know about the 741. Today's op-amps are much more complex than the 741, but the ideas are still the same with respect to having a differential amplifier followed by some gain stages and finally an output stage. And if you took EECS 412, you'll understand the ramifications of each of those stages. But these elements, transistors, diodes, linear circuits, they're important to us in EECS 622, but they are not sufficient for what we're trying to accomplish. To design systems like microwave receivers, radio receivers, we are going to need components that we have not studied before, you have not studied before, microwave components, things like couplers and mixers and such. We take those devices and we can put them together into a system, a microwave system, which can do useful things like receive a signal and present the output of the recovered information to some processor. So these are the kind of components and the symbols that you'll see in this class. And of course, we need to talk about them, understand what each of these devices do and why they're important in our designs. One of the goals I have for this class is to give you some sense of the history of electrical engineering. It always strikes me that, mathematicians know the history of math and all the famous mathematicians of the past, likewise for physicists or artists or any number of professions or avocations. Everyone knows their history. When it comes to electrical engineering, though, there is a rich history in the past, yet very few current electrical engineers know very much about electrical engineers of the past. So I want to talk about that. One of the things that kicks off from that is the history of electrical engineering systems. Certainly, the telegraph was probably the first that was impactful to society. Then we had telephony, telephones, power, generating electrical power to be able to do things like provide heat and light was also very significant. But I would argue that the most significant electrical engineering system in history has been the design of the first radio. And by significant, I mean from the standpoint of changing people's lives from the time prior to that system to the time after. Certainly, I don't mean the most sophisticated or the most developed technically. This device here, of course, is far more developed. Though this is a radio, it's a very sophisticated one compared to the early radios in the early 20th century. And again, by what I mean is significant is the impact to society before and after. So I know someone who was a child in the Ozarks of Missouri on a hardscrabble farm back in the Depression, grew up during the Depression in the 1930s, and a poor farm, and again in the Ozarks. To a certain extent, that family that lived at that farm lived precisely the same as families 100 years or 500 years, even 1,000 years prior to that. They had no electricity. Heat was Heat and light were all generated by fire. They had no telephones. There was no refrigeration. You kept perishables down in a well. You got water by pulling out of a well. Of course, from restrooms facilities, there was an outhouse out back. So if you want to take a bath, you had to heat up the water on the wood-burning stove and then dump it in a big bathtub on the kitchen floor. Saturday night was always bath night, apparently. So again, in almost every way, people lived back then similar to what they had 100 years earlier, but with one exception. And that exception was radio. If you went around to these farms that had no other utilities, attachment, no running water, you would find in most of them what's called a farmer's battery. A farmer's radio. It was an AM radio that was sitting there in the front room, and there were 2 or 3 lead acid car batteries sitting there underneath, and that's where they got the power from, was from lead acid car batteries. These radios were not cheap. They were several $100s. And of course, back in the Depression, that was a lot of money. Several months' wages for many people. Yet they had these radios. Now, I know this because this child I'm talking about, that grew up in the Depression in the Ozarks of Missouri, is my father. And when he told me that he had a radio growing up in the 1930s and they listened to the radio, I was surprised. I said, Dad, you didn't have any utilities at all. You had, your restroom was a hole in the backyard. Why did, Grandpa and Grandma spend the money to buy an AM radio? That seems quite superfluous. And he said, and I'll never forget it, he said, no, you don't understand. He said, everyone who could afford to get a radio would get one. They'd borrow money. It was like buying a car, but they would do it. Because if you're out on a farm in the Ozarks by yourself, you're completely isolated. Maybe you'll get a newspaper delivered to you once a week, or a magazine to read about things, but otherwise you feel completely disconnected from society. And then all of a sudden, here comes the radio. And you put it in your front room, and you can turn it on, and you can listen to the President of the United States give a fireside chat. Or you can listen to the St. Louis Cardinals play a baseball game. You can listen to crop reports and weather reports. You can listen to entertainment, hear Bing Crosby sing or Jack Benny tell a joke. And he said that changed everything, and it made life so much more tolerable to be out in the middle of nowhere during that time. And so everyone that he knew that could have any money at all would scrape together to buy a radio. And so we look at all the things we have now, or Insta Snaps and chat rooms or whatever they are that we have, and Facebook things that we can't live without, and we think that they're really quite the technology or transformational. But yet nothing, I don't think, in human history from a communication standpoint has changed the before and after as significantly as the advent of wireless radio. So if you're out living in this cabin, and all of a sudden you could get a radio, it would really change the quality of your life significantly. This little girl here, by the way, is my grandmother. Look at this ad right here. This is from an advertisement from the 1930s. And it's RCA, Radio Corporation of America, and they're selling a radio. There's a couple things that are interesting about this advertisement. First of all, if you look at the price down here, it's hard to see. It's $550, $550 for an AM radio. How many of you would spend $550 for an AM radio now? Well, this is back in the Depression, again, where $550 might be several months income for many families. The other thing about this radio, or this advertisement, is underneath the title here, it says Super Heterodyne. And the text, in fact, starts with the new Radiola Deluxe Super Heterodyne 64 is the finest receiving and reproducing instrument that has ever come from the Associated Research Laboratories of General Electric, Westinghouse, and RCA. So it's interesting to me as electrical engineer, it's talking about a receiver architecture, the super heterodyne, a design by a very famous electrical engineer that we will talk about later. And you're thinking, well, back in the 1930s, they had the super heterodyne receiver design architecture, but that was almost 100 years ago. By now, it's changed completely and completely obsolete. Well, it turns out that's not the case. Much of the original architecture of radio receivers and how radios behave in terms of sending information one to the other is still the same today as it was back then. The ideas are fundamental and they work, and there really is not been a change in the basic concept of how we design a radio receiver. So we will learn about the superhet in this class, and in the end, most semesters, I should say, you would design a superhet receiver as a class project. In addition to the superhet, which is still the prevalent receiver architecture of radios today, we'll find that the components of the superhet are still fundamentally the same as they were in early radio of nearly 100 years ago. Now, this makes it sound like what we're going to study is going to be ancient technology, and we should be studying something that's more up to date. Certainly, modern radio components are much better. They're smaller, cheaper, much more reliable, much faster, better performance in every way. That's been the theme, of course, of electrical engineering. We've gone through and we've made our components better and better, smaller and smaller, faster and faster, cheaper and cheaper, and more efficient. Not by 10% or 100%, it's by orders of magnitude. And so we couple the improvement in components of radio engineering to digital computing, which the primary artifact of that coupling is your smartphone. We're combining radios and computers together. We find that there are more radios in use ever before. There are more super heterodyne receivers being designed and manufactured than there ever has been in human history. So in this class, I'll use as an example of radio FM broadcast. And the reason for that is because everyone is familiar more or less with an FM radio, FM broadcast radio, if you've ever driven a car and tried to tune into a radio station, although that's happening less and less nowadays. But hopefully, at least for until I retire, that students will recognize what an FM radio is and an FM radio station is. And so I use that as an example. But this class is not studying specifically FM broadcasts. It's a very tiny niche of radios nowadays. Instead, we have a huge amount of radios that are being produced and designed out there, and very few of them have anything to do with AM or FM broadcast. Again, I'd use it as an example, but it's really a surrogate for a plethora of other kinds of radios that are being designed and built. And so, examples of wireless transmission of information include Wi-Fi links, obviously your smartphone's connection there, satellite radio, GPS that we have, smart watches. Even the other day I bought a few smart light bulbs so I can go through and from my phone turn on and off my light or dim it or change its color even. So more and more we see that wireless connections, and they all have transmitters and receivers, and basically using the same technology or the same ideas, same architecture as those designed almost 100 years ago. And this abundance of radio receivers goes beyond simply the commercial or consumer products that you are familiar with. There are lots of other radios that are built out there that you probably don't own. Satellite communications, radars. Here's satellite communication with the dish TV, cell phone towers. Ultimately, these are radio transmitters and receivers at the top of the towers. RFID is another application that requires a transmitter and receiver to use. So there are a lot of applications beyond simply the consumer products that you are familiar with, involved with navigation, sensing, and identification that likewise use radio frequency technology. So what is a radio? Well, an academic description of a radio is a device that transfers information to a distant site by means of unbounded electromagnetic propagation. So the radio has radio system, I should say, has three sections associated with it. One is the transmitter, which we shall see takes information and places it on an electromagnetic signal before it's propagated out of a transmitting antenna. The propagation channel, which is the space between the transmitter and receive antennas where the electromagnetic wave is propagating. And then finally the radio receiver, which collects some of the propagating waves and sorts through the received signals and strips off the information that is ultimately trying to be sent. So let's look at each one of these sections individually. So here's a block diagram of a transmitter, and all I'm trying to do here is sort of introduce these to you and give you some idea. Again, we have the remainder of our course to sort through these devices and how they work and how they're put together. But the radio transmitter actually is fairly simple. It has an RF source, and so we have an oscillator device which will generate a sinusoid, a high-frequency sine wave, and these are the vehicle that we use to send information from one place to the other. The sine wave by itself, it's a high frequency, but it has no information. If you just isolate it by itself, it's just a tone. We take information signal, and in the old days this used to be an analog of an audio or video. Now it's for the most part an analog of some data, some digital stream, and we take that information and we combine the signal into a modulator, and this has the duty of essentially gluing the information that we want to send onto the RF source. So what comes out of the modulator is what we call a modulated signal. We've modulated, changed either at the magnitude of the sinusoid or the phase of the sinusoid in a way such that it mimics or preserves the information of the original signal we're going to send. So we modulate the signal. If you take EECS 562 communication theory rather, you'll learn more about this. So now we have our information glued onto our RF source. The problem is it doesn't have enough energy. We were to propagate it now, we wouldn't get very far before it became unrecoverable or indiscernible. And so we take that signal, we run through a power amplifier, and we give it a lot more energy. And then once we have a high energy sinusoid with information glued on there via modulation, we send it to the antenna, and the antenna launches it out into space. So what happens once the electromagnetic wave is launched from the transmitting antenna? Now it has to propagate through space between the transmit antenna and the receive antenna. Now, ideally, this channel that we call it between the two is full of nothing. It's free space. The electromagnetic wave will propagate unimpeded from one point to the other. The amount of energy that it has, energy density, once it gets to the receiver, is dependent on the separation between transmitter. How far does it have to go? As it propagates along, it loses power at rate that quadruples every time the distance doubles from its previous location, 1/r squared. It falls off. Well, that's the ideal case. In reality, our channel now is full of stuff. There are buildings and trees and mountains. In addition, the atmosphere is full of other things like dust and rain and even gases in the atmosphere. And all of these will interact with that electromagnetic wave. It'll modify it. There's all kinds of electromagnetic phenomena that are interesting that happen: scattering, refraction, reflection, diffraction, extinction, all kinds of things that happens to the wave. We can keep a physicist quite happy for a long time examining all of these phenomena. What we find is, to the extent that these phenomena affect our propagating wave, depend on largely the frequency of the signal. As we go up in frequency, we get good things happen. The size of our transmitters typically becomes smaller, antennas become smaller. There's lots of things we like about going up in frequency. But the problem we run into is the channel will become more opaque, generally speaking, as we go up in frequency. Instead of propagating through it without very much concern, we find as we go up in frequency, these phenomena will start to cause problems. One of the nice things is, as long as we keep relatively low frequency, and by frequency, what are we talking about here in microwave? Well, we're talking about megahertz, which is hundreds of cycles per second, hertz being 1 cycle per second, hundreds of megahertz, up to a gigahertz, which is 1 billion cycles per second, all the way to 10 to 20 gigahertz. And so these are very fast cycling waves, sinusoids there. If we are below, let's say, about 2 gigahertz or so, what we find is most of the stuff that the wave encounters will look more or less transparent. We can propagate through it without much interference, and that's why you can take your cell phone and go in your room and shut the door, yet still get the signals from your cell phone. You can be in the basement of your house and still pick that up. It's because your house more or less looks transparent to a sinusoid at lower frequencies. It propagates through without much interference. As we go up in frequency, though, these things again start to look more opaque, and so ultimately there's going to be a limit on how high we can go in frequency. The third element then, and the most complex and most important probably, is the radio receiver. So we have an antenna, receive antenna, and that couples in the signal that we're interested in. And then we have a set of components here which do a number of different things. We have amplifiers, filters, something called a mixer, an oscillator, an IF filter, for example. Now this is a very simple superheterodyne receiver. By itself, it actually probably wouldn't work very well. We need to put some more complexity in there. But this gives you the basic idea. Now, don't worry that you don't understand this. This isn't the last time we'll talk about superheterodyne receivers. We'll spend a month at least talking about them, and almost the entire course talking about the component parts that fit within them. So this is just kind of background motivation of where we are headed. But in the end, we take the signal that has the modulated information on it, and we get through a receiver and we present that signal to a demodulator such that it can recover the transmitted information. So we take the modulated sine wave, it goes in the modulator, and out comes the signal. Now, why can't we just connect the demodulator right to the antenna? Why do we need all these other things? Well, we have to condition the signal before it gets to the modulator. One, we have to make sure that the signal that it goes to the modulator is powerful enough. One, we have to make sure that the noise going into the noise going into the modulator is sufficiently small. And 3, and perhaps the most difficult, is to make sure that only the signal we're interested in arrives at the demodulator. We can't give the demodulator several different signals because it has no way of knowing which one is important, which one has the information that we desire. And so we have to go filter out all of the other signals. And that's the real problem. Unlike the transmitter, where you're sending out one signal, on receive, you're collecting the signal you want in addition to every other signal that's been propagated that is out there. And that is the problem when it comes to radio system design, is being able to separate the signal you want from those that you do not. Again, that's the challenge in electrical engineering with respect to radio systems. We have many, many transmitters out there. In addition to all sort of broadcast and communication towers, every element now, your cell phone, your Wi-Fi, everything is a transmitter sending out energy. And so if you receive electromagnetic energy into your receiver, you're collecting theoretically signals from all of those. And what we have to do is sort through and pick the one signal we're interested in and condition it to be demodulated while basically rejecting or suppressing all of the other ones. And that turns out to be a very difficult process. And the receivers we have designed are a little bit complex, not again in any one particular step, but a series of steps that will lead to the outcome we desire. One signal, the desired signal, being at the demodulator, all other being rejected. That's why radio engineers ultimately make the big bucks. The obvious question then is, by what mechanism can we sort through these signals? By what criteria or artifact do we choose the signal we want and disregard to suppress the signals that we're not interested in? And ultimately that criteria, that artifact that we're looking for to do the sorting, is its signal frequency. As we talked about in the transmitter, the first thing we do is generate a sinusoid at some frequency, somewhere from the megahertz all the way through the gigahertz in terms of oscillating frequency. But it just has one frequency, one pure tone, one sine wave that stays exactly at that frequency. That frequency is what we use to sort through. So for example, and I use this example all through the course, again, of FM broadcasts, let's say we're wanting to tune to the FM radio station 101 The Fox. All right, it's down there in Harrisonville. It's a classic rock station, and it also broadcasts the Chiefs games during the fall, or at least it used to anyway. And so let's say you are driving down the road and you want to tune your radio to listen to 101 The Fox. So what does your FM radio receiver do to select that signal? Again, what it's looking for is simply a sinusoid at a frequency of precisely 101.1 megahertz. And it has to be very precise. So it's looking for 101.100000000, exactly a sinusoid at that frequency. What we'll find is there's all kinds of signals that are all around that frequency. And of course, we don't want to listen to those radio stations. Not only do we not select them, we have to suppress them before they get to the demodulator. So our job is, again, to reject all signals propagating at other than 101.1 megahertz, but simultaneously amplify the signal that we're interested in, the one at 101 The Fox. So this is a hard task. The reason that's a hard task is there's so many transmitters that are out there. Certainly nowadays, as we've talked about, there are literally millions of devices out there that transmit electromagnetic energy, if not tens or hundreds of millions of devices that are. And they all can theoretically make it to the input of your receiver, of your FM receiver, for example. And that receiver has to be able to reject all of them, save the one that you're interested in. So it's not just simply rejecting all the other FM radio stations. It's rejecting all the signals that are being radiated at any and all other frequencies except for 101.1 megahertz. So the analogy I use here is, let's say we're at Allen Fieldhouse, and let's say Allen Fieldhouse is full of people and they're all talking, and you're sitting there at center court, and you want to hear the conversation, what somebody is saying, all the way, let's say, up here in the rafters in the very top of Allen Fieldhouse. Now this is a problem. It's a problem for two reasons. One is, even if there weren't any other people there, this person is talking too softly for you to hear. The other problem is, of course, everyone else in the arena is talking at the same time. Some of them may be talking very loudly or shouting even. And so how in the world could you go through and listen to one person way up in the rafters and understand what they're saying when you're all the way down here at center court, given that, again, they're not speaking very loudly, but the entire arena is full of people that are. That's really analogous to the problem we have in receiver. The signal we're interested in, again, is very small. It's a long ways away, and there are all kinds of other signals that are very loud, and they all come into the receiver, your ear, and how do you sort through them? Well, the reason that we can sort through them, unlike the audio example we have here, is that each transmitter, each person speaking, has their very own signal frequency assigned to it, and we use that as the parameter to sort through and suppress ones we're not interested in and amplify the one we are. So in the end, what we want at the output of the receiver is a situation where the signal appears like this one person up here is the only person. There are no one else making any noise, and that person, the one person that we're interested in, is now shouting their message so loudly that it is easy for us to understand what they are saying. So we come into the receiver, again, with many people talking, and the person we're interested in talking speaking very softly. We come out of the receiver with the voices, all the other voices rejected. A single voice, the one we want, is retained, and that voice has been amplified to the point where it is easy to be understood. That's metaphorically what we try to do in a receiver. It appears we have a problem when you think about it. If there are literally tens of millions of transmitters out there, and each one has to have a different frequency, signal frequency, so we can sort through them accurately, that implies that we would need, tens of millions or hundreds of different frequencies assigned to these signals. And the question then becomes, is there enough of these transmit frequencies to go around? And the answer really nowadays is no, there's not. The spectrum is very crowded, and it's so crowded that it needs regulation to make sure that every transmitter, every frequency is associated with one transmitter and one transmitter only, effectively, in some region, so that signal can be identified and modulated. The governmental agency that's tasked with the regulation of our spectrum, of assigning these frequencies to each transmitter, is the Federal Communication Commission. And it used to be sort of a mundane, nondescript commission that no one paid much attention to until, of course, cell phones came along. And then all of a sudden, bandwidth became very valuable, and it became very contentious in terms of allocating the spectrum. There are many different transmitters for many different applications. As we talked about earlier, in addition to communication, there's sensing and navigation, and radio astronomy, which essentially is the absence of signals there, but they need to make sure that nobody is transmitting at certain frequencies, for example. And so the FCC goes through and allocates different bands for different users. And again, that used to be a little bit less contentious, but now, because of the huge demand of wireless systems, and particularly because of cellular systems, there is pressure all the time on the FCC to convert some bandwidth, some frequencies that are allocated for other users, into frequencies that can be used for cell phones. And of course, those people that lose their spectrum are not very happy about it. But that is the job of the FCC, is to make those determinations. Once they get more spectrum opened up for wireless, for cell phones, for example, the latest now is 5G coming along, and so they're allocating spectrum for 5G. Once they decide that there's certain spectral bands that are going to be for 5G, then the question is what company gets to use them, because again, ultimately there's a transmitter, and that's assigned to Verizon or whoever, T-Mobile. Would have said Sprint, but I guess Sprint no longer exists. And the FCC has found that the best way, perhaps, to go through and figure out who gets the spectrum is who wants it the worst, and who wants it the worst in terms of actually writing a check. And so there's these big auctions where the FCC auctions off something that's ephemeral, the spectrum they don't really own, but they regulate. And so the right to broadcast at certain frequencies is put up for open bid, and they go for a lot of money. So now the FCC is sort of one of the few parts of the federal government that actually generates revenue for taxpayers. To show you the complexity of the problem, you might want to look at the FCC frequency allocation chart. And this is very busy and very small. You can't, there's no way to put it on one sheet of paper so you can see it all. I would recommend that you Google it. You can look it up and bring up PDF files, or you can look at these with a little bit more resolution that I have here. But these bars, as you go across, are different parts of the spectrum. And then these basically go up in order of magnitude. It starts down the kilohertz and ends up here into the millimeter wave, multiple tens and even hundreds of gigahertz there. And throughout each of these spectrum, you see blocks of different colors, and each block corresponds to a different application. And this is how the FCC has split up the spectrum and allocated. And again, once they allocate parts of the spectrum for, let's say, mobile, then there's a question of which mobile carriers get the specific frequencies there, which is where the auction comes in. But I think this is interesting to look at, and it sort of tells the point. Here's an expansion here of just this little region right in here. And this goes from basically 2 gigahertz all the way up to about 2.8 gigahertz. And it shows the different allocations, different bands. Here's amateur, radio location, mobile, let's see, what else is in there? It's hard for me to read. Space operation, satellite. And so they're split up into very small bands, and some bands have multiple applications that are assigned to them. But if you look at these bands, for example, this one goes from 2.18 gigahertz to 2.20 gigahertz. So we're talking about very small bands that are broken up and then allocated to different applications. So it's quite a regulatory challenge to go through and do this. And again, I would suggest, and hopefully you will look this up on the web and spend some time looking at this radio spectrum, because it really helps understand what we're going to try to do in this class. Again, somewhere in this box there's going to be one signal that you are interested in, and you need to amplify that and reject all the signals that occur from all these different applications at all these different other frequencies. Now, you might argue that why is this a problem? We're talking about spectrum, which is simply a number that describes the frequency of oscillation of some sinusoid. If we run out of frequencies, how can we run out? We just keep increasing the number. We start in the megahertz, then we go to the gigahertz, and then we can go into the terahertz, for example, and just keep increasing the frequency and have plenty of spectrum to go around. But there are two problems with this. The first problem they run into is the actual components that we need to build transmitters and receivers. Like most things in electrical engineering, as we go up in frequency, two things happen, and they're both bad. One is the cost goes up, and the other is the performance goes down. And this is true pretty much in all cases when we're talking about components that behave on signals with certain frequencies. The higher the frequency you go, the more cost you get and the less performance, generally speaking. Not always, but that's generally speaking. So if I put a limit on what's the breakpoint where it's just sort of not practical to go beyond based on the current technology, I'll say around 20 gigahertz. Now, this is arguable. It's completely subjective. It all depends on what you say, what I mean by reasonable cost and performance, of course. This is probably moving upward. 20 years ago, I would have been very confident saying 20 gigahertz is the upper limit. In fact, might have been thinking that was stretching it a bit. Now we're starting to move into more higher and higher frequencies where we're moving up toward 100 gigahertz even with respect to components and things that are being built. So, this number obviously can change. The history of electrical engineering, of course, would argue that over time, this limit on technology, the component behavior and cost, will get better and better. Again, we started, let's say, at 20, and now we're starting to push that up. And you can argue that would continue, that we will continue to have components that work better and are cheaper as we move up in frequency, as electrical engineers do their thing and improve things by orders of magnitude. So here's an example of that. This is an ad from, I think, in the 80s kind of thing, probably the late 80s, perhaps early 90s. The hard disk you've been waiting for, the memory that you've been waiting for. It has, it's $3,400 for a whopping 10 megabytes of memory. And of course, this is laughable now. You could get, terabytes for a few $100s now. But back in the 80s, this was, this is quite the deal. And of course, the reliability, this wasn't particularly good, and it wasn't very small. The history of electrical engineering is one of improvement, not by percentage, but by orders of magnitude of being 100, 1,000, 10,000, a million times better than what it was just perhaps a decade or two before. And so we might conclude that that would continue for microwave components. But as I said, there's a second problem involved with increasing the upper end of our spectrum, our usable spectrum, and that's one that electrical engineers can't do anything about. We talked about earlier the fact that our electromagnetic waves, our transmitting waves, must propagate through the Earth's atmosphere. And that's a consequence of the fact that primarily communication is from some human on the Earth's surface to some other human on the Earth's surface. And because of that, we're going to have to spend time propagating through the Earth's atmosphere. And the Earth's atmosphere is largely full of stuff. Even if we ignore things on the surface like buildings and mountains and trees and such, as we go up higher, the atmosphere is oftentimes not clear, and it will have to propagate through that. And we alluded to earlier, as we go up in frequency, the interaction of our signals with these elements will become more problematic and more difficult to propagate through. If we stay below 5 gigahertz, and that would be, again, 5 billion cycles per second, then the Earth's atmosphere almost always appears to approximately be a vacuum. You don't have to worry too much of interaction of the electromagnetic wave with the atmosphere itself. And of course, that's a large amount of spectrum. 5 gigahertz, 30, 40 years ago was probably all you needed. The only thing that would be higher than that would be things like radar, for example, might want to go higher than that. But as we've talked about, the fact that the spectrum is getting so full that we're pushing far beyond 5 gigahertz. From 5 to, let's say, 18 or 20, we find that the atmosphere is pretty transparent, as long as we don't have precipitation. Rainfall is the primary one that will mess things up. And if you have a dish TV or any kind of a satellite communication, but the dish TV, that's what happens when it starts to rain. If it starts to rain too hard, you can lose your signal because it's too high a frequency that it's using to propagate through the atmosphere when it's full of water droplets. As we increase the frequency, though, even if it's not raining, we find the constituents of the atmosphere, even on a clear day, will be such that the atmosphere will begin to look opaque. It'll look sort of foggy. And as we go higher in frequencies, it'll get to the point where essentially it looks completely opaque and you cannot propagate at all, even though to us in the optical region it looks like a perfectly clear atmosphere. In the microwave region, there are frequencies where we cannot get through, and that ultimately puts a limit on our spectrum that is usable regardless of the technologies that we've created. So this chart hopefully kind of explains the phenomena of frequency versus extinction or absorption as we pass through the atmosphere. The reason that the atmosphere looks opaque is essentially the atmosphere will rob the energy of the propagating electromagnetic wave. There's a power density, watts per square meter, associated with any electromagnetic wave, and as it propagates along, it will diminish if the properties, the constituents of the channel can absorb that energy. And as we go up in frequency, we find that many of the constituents will become very good at absorbing that energy, robbing the energy from the signal to the point that it is not recoverable even after a very short distance. And so we look at this plot here. Horizontally, this is the frequency of the signal in gigahertz. Notice this is a log plot, so this is 1 gigahertz, 10 gigahertz, 100 gigahertz, 1,000 gigahertz. And so certainly under 100 is where we typically find any sort of radio wave propagation that is useful to us. And as we go up, this is attenuation, and this is in dB per kilometer. By how many dB is the power density diminished if we were to propagate 1 kilometer? That's what it says. Now, dB, of course, is a decibel expression of that attenuation. This vertical scale is likewise a decibel representation of dB, 10 to the minus 2, 10 to the minus 1, 1, 10, 100, 1,000. And so this is a double log representation of attenuation, and that really is required to sort of put all the points onto this plot, because what we find is attenuation will rapidly increase as we go up in frequency beyond, let's say, 10 gigahertz, and for a number of reasons. First of all, we look at this dotted green line, that's heavy rain. And the other dotted green line is light rain. And as we find, as we move toward 10 gigahertz, the attenuation starts to get to the point where it's, 1 dB per kilometer. Well, if you're a satellite and you're going for a lot of kilometers, then that dB can stack up to where you may have attenuation of 10 dB or 20 dB or 30 dB. Well, attenuation of 10 dB or 20 dB is a reduction of 99%. 30 dB is a reduction of 99.9% of the power density. So as we start to move in this region here, we really start to see a huge diminishment in the power density, and that can happen again as we start to move around 10 gigahertz when it's raining. Now, as we move up further toward 100 gigahertz, what we start to see are these curves. And what are these? Notice each of these curves has sort of a chemical associated with it. We have oxygen O2 for this sort of burgundy-looking curve here. The black curve here, notice, is water vapor, H2O. These are gases in the atmosphere. At low frequencies, they don't absorb any energy at all. They look completely transparent, invisible to us at these low frequencies. But as we start to move up into the gigahertz region, tens of gigahertz, 30, 40, 50, toward 100, we start to see that there's this peak in the attenuation. So these are what we call absorption lines, and this really gets back to quantum mechanics, where the energy absorption can happen for certain frequencies there. At certain frequencies, they can absorb, not only can they absorb energy, they will absorb energy at a great rate, and it becomes very difficult to propagate through even a very short distance at those frequencies. For example, right around here, I don't know what that would be, maybe 50 gigahertz or so, I can't remember now, we have an oxygen line that peaks up all the way to 10 dB per kilometer, which means that every 10 dB your signal diminishes by 90%, and so you can't go very far in that situation. As we move up into the hundreds of gigahertz, we really start to have a problem with water vapor. Any humidity in the atmosphere then will absorb energy, and these peak up at 1,000 dB per kilometer. 1,000 dB, and it's, I don't even know what that is. That's basically zero, and you can't propagate. You can't hardly propagate millimeters through that atmosphere if you get up to, let's say, 1,000 gigahertz because of water vapor. In this region here, essentially the atmosphere is completely opaque, completely dark. You can't see through it at all with frequencies in this region, and so that really limits then how much we can increase the frequency of our transmitters. As we get to 10, we start to become problematic. We get to 100, it becomes, beyond that, really almost impossible. What we find nowadays, 5G is trying to push into this region between 10 and 100 gigahertz, and they're doing this by keeping the wireless transmission distances small, to which just in a kilometer or less. But even then, if they start to have a problem with rain, your 5G system, they don't advertise this, but your 5G system, if it starts raining really hard, is probably going to have issues, and that's why 5G has backup down in the lower frequency spectrum. So if rain does knock it out, they can switch to that and sort of have diminished capability, but at least capability nonetheless. Interestingly, if you move along, you can see the different spectrums here. S8 is, let's see, EHF is extremely high frequency. This is the infrared. And then you see visible light up here. And at visible light, we see that the attenuation due to the atmosphere has dropped back almost to nothing, almost the way it is at the other end. And of course that makes sense. We know when we have a clear sky, it looks clear. It looks like there's nothing there. And that's good news for us. If visible light were just all kind of back here, down here in the region where we had a lot of absorption due to oxygen, the planet would be a very cold place and could not sustain life. But instead sunlight is just beyond that, and so we can get sunlight to the ground and warm the earth and nourish the plants and so forth there. Just below visible light, we have infrared, and notice there's a region just below it that is fairly clear. And so there are a lot of radios built at infrared. There's still propagation issues, but we use them, and primarily those radios go over a short distance, the distance between the couch and our TV, which we use infrared radios essentially as remote controls, and so they exist in this region, just below the visible region, so we can't tell they're operating. They don't annoy us with their light, but the propagation through the atmosphere is still very good, and so they can become usable at that region. To reiterate then, as we try to increase the signal frequency of our propagating signals, try to increase the spectrum by increasing the frequencies that we transmit, we run into a practical limit, a pragmatic and practical limit, which is the atmosphere. And there's nothing we can do about the atmospheric physics. It's due to quantum mechanics, and even people as smart as electrical engineers would not be able to alter that. So there is a pragmatic limit, upper end, to the spectrum that we can work in. I would say arguably it's around 40 gigahertz, but like I said, 5G is actually trying to push beyond that, I think into 60 and 80 gigahertz. But those channels will be somewhat unreliable depending on whether, again, it's raining hard outside or not. And so they have backup spectrum at lower frequencies for those cases where they can propagate in a diminished capacity. So this is just a summary of what we're up against again with respect to radio engineering. We're trying to pick out the one signal we're interested in, diminish all the rest of them. It's a very crowded spectrum. The spectrum has upper limits based on the pragmatic ideas of technology, performance, and cost, but ultimately in terms of the atmosphere that we propagate through has a limited bandwidth itself.